it's cold out tonight. I hope you're staying toasty, calculus nerds like me. So we've looked at disks and washers. Tonight we're going to look at shell method. So if I was doing this the old way, where I'm using disks and washers, I would say I'd need to split this up because I see a gap up here at the top between my spin axis and y equals x squared plus 1, which would make me want to use washers. But I notice at the bottom that down here, the bounded region actually touches the y-axis. So for that section, I'd want to use disks. And I could in fact do that and add them together, and voila, I'd have my volume. But the question is there another way that might be a little more efficient instead of dividing it up? And the answer is yes, there is. It's called the shell method. So imagine that I'm lining up a whole bunch of soda cans inside each other, and they get progressively shorter to make up this bounded region. So these are all the heights of my soda cans, and I just keep lining them inside and inside. So those are the heights. Now, for the particular one that I had drawn to start with, of course, it has a radius. And if I want to actually figure out how much that radius is, I would do right minus left. Well, this right is some x value. I don't know, because for each cylinder, it's a different x value, but the left is always 0. So my radius is just x. And then for the height, I would want to do top, well, that's my original equation, x squared plus 1, minus the bottom, but that bottom is just 0, so my height is x squared plus 1. And then the thickness of these shells is just my dx. Now, if you imagine that I'm taking all of these soda cans and I'm lining them inside of each other, then really, when I open them up, I'm really just looking at the surface area for a cylinder. And if you remember all the way back to geometry, I'm sure you do, the surface area formula for a cylinder was 2 pi RH. And so I'm going to take a whole bunch of those. That means I'll have to integrate in order to add up all of their surface areas. Now, one more thing that I like to note is I was spinning around the y-axis, and notice my height is parallel to that. And I'm always focused on height. So if height is parallel to y, then I'm doing dx. I really think about it as, where's the height perpendicular to? Oh, it's perpendicular to x, then I'm doing dx. If the height was perpendicular to y, then I do dy. And that's, of course, how I generate the volume formula, is I use this surface area, which is circumference. So there's my 2 pi r, times the height, there's my h, and then, of course, the thickness is either dx or dy, depending on which way I'm spinning. And oh, for you people that love to memorize, here you go. So if I'm parallel to the y-axis, my height, of course, then I'm integrating with respect to x. And if that height is parallel to the x-axis, I'm integrating with respect to y. Of course, on the dx side, radius and height need to have x's in them, duh! And I'm using the x bounds, all because of that dx. And over on the other side, if I'm integrating with respect to y, then radius and height have to have y's in them, duh! And I need to use the boundaries for y. And I know you're just dying to get started, so let's do example 1. You graph it first. No, you graph it first. No, you graph it first. Okay, let's graph. Okay, so remember, if I'm spinning about the y-axis, my height has to be parallel to that. So my height would be some random location in here, which means my radius is going the opposite way so that they're perpendicular. And so now, if I want to find them,